All right, good morning. Welcome back to day number 3. And today we'll start with Mark, who will tell us about one-shot signatures. Please take it away.
All right, thank you. So I'm excited to tell you about this really cool thing called one-shot signatures and some recent work on it. We'll get to one-shot signatures later. I'm gonna lead with 3 very interesting questions. So the first one is, let's suppose Alice has some quantum state, and I want it to be like an interesting, inherently quantum state, so not just some quantum state that happens to be a classical state. And she wants to send her state to Bob, except she can only use classical messages to talk to Bob, and they have no pre-shared entanglement. So nothing like, you can't do quantum teleportation or anything like that. So is there a way for Alice to send her quantum state to Bob for some interesting family of states? And one particular example that would be very interesting is if this quantum state happened to be quantum money. So quantum money was originally proposed by Wisner, and it's basically we use the no cloning theorem in order to protect your money against counterfeiting, rather than relying on the inability to recreate a fancy piece of paper or something like that. So the question is, can you send quantum money with classical communication? And the point is, quantum money is an inherently quantum object, so it's non-trivial to think about trying to send it with classical communication. So we can look at this question from a few perspectives, and if we just look at the information theory alone, really this is impossible. Why? Well, we know that a family of states can only be sent with classical communication. And I'll use the word telegraphed just to distinguish it from teleportation, because teleportation has a kind of well-understood notion. So I can only send quantum states across a classical channel if those states happen to be orthogonal. This is if and only if. And moreover, if you have a family of orthogonal states, you can apply unitary to them to rotate them into the computational basis. So what that says is really if there's anything that you can send, then it's really not an inherently quantum state, it's really just a classical state in disguise. So not super interesting.
Doesn't that already apply to the Wisner money scheme though? Like the bank knows how to prepare the state, so it can send someone instructions on how to prepare the state.
Yeah, the bank can, but if I'm the bank and I give you a money state, can you then send it to someone else? Yes, that's okay, really
so the word unknown is showing up somewhere in here, right? Like if I have a circuit to make the state, then obviously I can.
Yeah, exactly. Yeah. Okay. Okay, so that was information theory. Says no, you can't do this. However, we live in a world of computationally bounded algorithms. And so another natural perspective is to look at this from the perspective of complexity theory. And here all bets are off, right? So one is orthogonality is actually not sufficient for telegraphing. You can have families of orthogonal states that you can't send with classical communication. Just because it's computationally intractable to kind of get the classical messages you would need to do that. And on the other hand, orthogonality does not imply efficient transformations to classical states. So even if your states are orthogonal, information theoretically, we know we can rotate them into the computational basis, but computationally, this might be infeasible. So there's still some easy things you can show you can't do with classical communication, but in general, for just this task of sending quantum states, with complexity theory, in that view, there actually could be interesting things you can do here. And I'll mention that there's a lot of works kind of in this general setting where you're allowing only classical interaction between parties, but doing something interesting at a quantum level. But none really directly address this question. So one kind of family of works is quantum teleportation and a bunch of related concepts. But these all rely on pre-shared entanglement. And here I'm imagining we have no pre-shared entanglement because maybe we think that the entanglement doesn't last very long and we're separated and can only send classical messages. And another family is remote state preparation. There's been some work in the complexity theoretic setting where you have a classical client that gets a quantum server to prepare some quantum state using only classical information. But here, we're pretty much always working in the setting where the sender actually knows the classical description of the final state that the receiver gets. And really what we're looking for here is a setting where the sender actually doesn't know the state, or at least doesn't know enough information to actually reconstruct the state, and is yet somehow able to send it to Bob. All right. Okay, so that's question 1. Now let's get on to question 2. So we have a setup where we have Alice and Bob, and they can't talk to each other. They have a wall between them. They don't share entanglement. There's nothing. They can't send any messages across. And they're receiving messages from some adversary. And what we want to ensure, what Alice and Bob want to ensure, is that they are actually getting the same messages from the adversary. That the adversary can't tell Alice one thing and tell Bob something else. All right? So can Alice and Bob ensure that the messages they get, M0 and M1, are actually the same without any communication? And if you just look at this, it's kind of clear that there's nothing they can do. They can't talk. There's really, the adversary can send M0 to Alice, send an arbitrary M1 to Bob. They will have no idea what was sent to the other one. There's no way to ensure consistency. So we need some sort of assumption in order to make something interesting happen here. And here's the assumption we're going to make. We're going to allow a setup procedure that produces what I'll call a verification key, but just think of it as some information. Produces some classical information that it sends to both Alice and Bob. And then it also gives some information to the adversary. And we don't necessarily yet need to think about this being a quantum question, but since we'll ultimately use quantum, I'm allowing the setup to give a quantum state to the adversary. But this verification key that goes to Alice and Bob is actually classical. All right? So there's this setup that allows Alice and Bob to this is the thing that allows them to coordinate, because now they know they have some common information, this verification key. And now what the adversary is going to do is when they want to send a message, they're going to append a little extra information, a proof, or in cryptography we call it a signature. And Alice and Bob will verify that that signature is valid using their verification key. And so what we want is that, okay, maybe Alice or Bob rejects, and then we don't care what happens. But if both Alice and Bob accept, we want them to ensure that the message that they get in the accepting case is the same. Okay, any questions on the setup so far?
Sorry, but what pre-shared information do they have, if any?
They just have this verification key.
Okay, so they have the same verification.
Yes, yes.
And, all right.
And we're going to make things even harder for us, and we're going to allow the adversary to do the setup. So the only guarantee, so basically the adversary controls everything. All the information that gets sent to Alice and Bob, everything is controlled by the adversary, except in the setup phase, we know that this verification key, the adversary created it, he could have done anything he wanted, but we know that Alice and Bob get the same verification key. And that's really the only guarantee they get. If you remove this guarantee, then we're kind of back in the setting where there's nothing you can do to ensure consistency. So at some setup point, we're ensuring consistency of this verification key, and then that guarantees that later we, regardless of what message the adversary wants to send to Alice and Bob, we can ensure this consistency.
There's some assumption about like the largeness of the key, because presumably if I gave both Alice and Bob a 0, that doesn't help.
I mean, so if the key is 0, you could just say Alice and Bob reject, right? And one thing to make this non-trivial, you could just say Alice and Bob always reject no matter what. That's like kind of a trivial solution here. To make this non-trivial, we want that if the adversary is fine with Alice and Bob getting the same message, then he can actually send any possible message to them. So he can run, there's some setup he can run, and then later send some message, and Alice and Bob will in fact accept that message, as long as it's the same.
So for example, if VK described a QMA verifier that had a unique accepting witness, that would do it.
That would, what do you mean that would do it?
Well, I mean, then then if Alice and Bob both accepted a state that using that verifier, then the states would be the same.
Yes. Okay. So one thing is I'm insisting on classical messages here, but another thing I should have made it more clear on the slide. I want this message to be only known after the setup. So the adversary sends VK first, and then later he decides on a message to send.
Oh. Okay.
Yeah, because otherwise you could just, he could just commit to the message here and then send it later.
Good.
Yeah, so so this should have said, after the VK, there's,
I see.
he can send any message he wants as long as it's the same to both Alice and Bob, but he can't send two different messages.
I see. Thank you.
Okay, any other questions? Okay, so let's look at it again from, our different perspectives. So first, from the information theory perspective, this is actually also impossible. Why? Well, the non-triviality condition says that, you fix the verification key, and it says for all messages, there is some mechanism by which the adversary can sign that message, can produce a valid signature or proof on that message. And in particular, that means it exists, right? So for every message, there is some signature on that message that will get Alice to accept, and likewise, that same signature will get Bob to accept. And so what that means is if you don't care about computational constraints, basically the adversary can just choose an arbitrary M0 and M1 that are different, and then just do a brute force search over the proof space to find sigma 0 that verifies M0 and sigma 1 that verifies M1. These are guaranteed to exist by the non-triviality condition. And then he'll just send M0 sigma 0 to Bob, M1 sigma 1 to Alice. By the non-triviality condition, Alice will accept this, Bob will accept this, but they're different messages. Okay? So from an information theory perspective, this thing doesn't make sense. And here, I'll also divide out into classical versus quantum complexity. So as I said, like this question makes sense to ask this question even classically. Just that thing that I called a secret key with the ket around it. Just imagine it being a classical string instead. And from a classical complexity theory perspective, actually, it's also impossible. So in the classical world, moving to a complexity theoretic view doesn't help you. And the reason is that if we're insisting that our adversary is efficient, not only does this sigma exist for any message, but there's an efficiently computable classical procedure that computes it from the secret key, which, in the classical world, the secret key will be a classical state, and the message. And so the same attack just works. It's just that you don't have to brute force your signature. You just compute it using this efficient algorithm that's guaranteed because we're only considering efficient adversaries. Right? Yeah, okay, so this is really an inherently quantum question, if it's even feasible at all. It's an inherently quantum question. And when you move to quantum complexity theory,
could we just say if there's two different messages that I could efficiently find, which there have to be for non-triviality, then I can send one to the one person and the other.
Yes, exactly. Yeah. Good. Now, when you move to quantum complexity theories, everything gets thrown out the window. Why? So we still have this non-triviality condition, which says that once I've fixed my verification key and the adversary has this quantum signing key, there's an efficiently computable quantum procedure that takes this quantum signing key in the message and produces the signature. So that still holds. However, now imagine trying to sign two messages. Well, signing two messages using this efficient procedure, it's some measurement on this quantum state. And these measurements, they might be incompatible. They might not commute. Which means that if I try to sign M0 to get sigma 0, I just applied a measurement, and I just destroyed my secret key, and now there's nothing that I can do efficiently, at least, to compute sigma 1. Again, sigma 0 and sigma 1 will always exist, but we're asking about can you compute them efficiently? And the non-triviality condition does not guarantee that you're actually able to compute these efficiently.
So if the secret key were classical, it's still hopeless?
Yeah, that was the previous slide.
Yeah.
I was gonna ask that because I thought the adversary controls the secret key and
Yes.
it's not available to the Alice and Bob. So
Yes.
somehow the verification key needs to give some verification that the secret key is quantum.
Yes, that sounds weird when you say it, but yes, exactly. So kind of an implicit in here is that the only way for the adversary to construct a verification key and then later sign a message to get a valid signature relative to that verification key, the only way he can do that is to have a quantum state. Now, maybe it doesn't actually look like, he might use a different procedure than what is guaranteed by the non-triviality condition. Maybe The non-triviality condition says it's a quantum state and he tries to measure it or he produces some other state, but it says no matter what he does, anything he tries to do to construct this verification key, if whatever he's left behind after he constructs the verification key, if it's not quantum, there's no way for him to sign a message.
Thank you.
Yeah. Any other questions? All right, so a solution to this question, we call them one-shot signatures. And these are a hypothesized notion that has a number of interesting applications. I mean, basically, if you think about it, like what a one-shot signature is doing is it's enabling some consistency check that doesn't involve direct interaction. And this turns out to have a lot of potential applications. Orsat has showed a number of applications to doing smart contracts without having a blockchain. You can think of a blockchain as like the mechanism by which different parties communicate to make sure that messages are consistent. But now with one-shot signatures, you can do away with the blockchain. Another cryptocurrency-related application is that there's these lower bounds for consensus protocols that have long been known. And one-shot signatures allow you to circumvent these lower bounds and potentially make like milder assumptions on who's honest and whatnot. And as we'll see at the very end of the talk, one-shot signatures allow you to develop a quantum money scheme that you can actually send with classical communication. And there's probably a number of other applications. So this is a really, really neat object. However, a priori, it's unclear if it should exist. So, the previous slides, I kind of explained, okay, you need quantum, you need complexity theory, and if you have both, it's not obviously impossible, but at the same time, that doesn't say that it should be possible. Maybe you just need to think a little harder, and in fact, there's a possibility. So that's what we're going to, work on today. Before getting into that, though, I have one more question. And this is going to be very different. So here, the question concerns cryptographic hash functions. So what is a hash function? It's a classical function, let's say efficiently computable. It takes very long inputs and maps them to very short outputs. Okay? So a collision in such a function is just any pair of distinct inputs that maps to the same output. And just by the pigeonhole principle, we know that there's tons of collisions in here, right? Like imagine this is like 2 to the n, this is 2 to the 2n. Each point on average will have 2 to the n pre-images. So there's tons of collisions in such a hash function. And a cryptographic hash function, so it's easy to come up with functions that map big inputs to small outputs. But for cryptography, what's really useful is if we can have such a function that's collision resistant. And that means that even though collisions exist, and there's tons of them, no one can find them. It's computationally infeasible to actually produce a collision. So cryptographic hash functions have tons of applications throughout cryptography. And I'll talk about one application here. This is kind of a toy setting, but it turns out that this setting is kind of an abstraction of a lot of settings that arise in cryptography. But this kind of strips out most of the annoying details and is just a very simple protocol. So basically, Alice and Bob, what they're going to do is they want to run a coin tossing protocol. So they want to produce a random bit and actually be guaranteed that it's random. And they're each going to try to bias it in different ways. So Alice wants the bit that gets produced to be 0, and Bob wants the bit that's produced to be 1. And so their goal is to try to bias this bit. And if you don't use crypto, it's not hard to see that whoever goes last can always bias this. But with crypto, you can do something interesting. So here's a simple protocol using a hash function to flip random coins. So what Alice is going to do is she's going to choose a random bit, BA, and she's just going to choose some other random string R. And she's going to hash, using this cryptographic hash function, she's going to hash it down to some small hash h and send it to Bob. So what you should think of this is as it's a commitment to the bit BA. She's committing to the bit BA, but she's not revealing it. If she revealed BA, then the protocol's not gonna work. So she kind of hides it by hashing it with the cryptographic hash function. So now Bob chooses just a random bit and sends that to Alice. And then Alice opens her commitment. So she actually just says, what is BA and what is R? And she sends that to Bob. And now what you can do is you can verify if that the BA and R were actually correct. So Bob can take BA and R, hash it down, check that it was, sorry, this should have been an H, check that it gets the H that Alice sent in the first message. And assuming this, so if this fails, we'll just output bot, special symbol bot, we'll just say we abort, there's no random coin, we give up. But if this check passes, then we're gonna set the output bit to be BA XOR BB, okay? Right, and again, where does the hash function come in? Okay, so if Alice just sent her BA and R in the first message, then Bob will just choose BB to be the opposite of BA, and he can just always bias the protocol. And if Alice tries to bias BA, well, she sends BA kind of hidden inside the hash function before Bob even chooses his bit, and his bit's random, so she can't really bias the protocol. That's the intuition. Okay. Okay, and then I want to point out that we're going to allow Alice and Bob to arbitrarily deviate from the protocol. So maybe this hash that she sent actually was not the hash of some bit BA and then some string R that she later reveals. We don't know what she does. She could do anything she wants. All we know is that at the end of the day, this verification happens. That hash of BA comma R will ultimately be this string H at the beginning, but we don't know how Alice actually came up with it. And likewise, Bob can do whatever he wants. He can, he doesn't have to flip a random coin. He can always set it to 0, for example. Okay, and a not hard theorem to prove, I won't show it, but is that basically that Bob can't bias the bit. So assume Alice is honest, that she actually behaves as she's supposed to. There's nothing Bob can do to bias the bit significantly. And intuitively, why is this? Well, remember that H is many to one. So it has all of these inputs that possibly map to the hash little h that Alice sends. And in particular, with a little more work, you can show that that actually the string H she sends is actually statistically independent of her bit BA. That it literally, from an information theory perspective, just completely hides Alice's bit BA. And so no matter what Bob does, the final bit is the XOR of his bit, whatever it is. You can set it to 0, you can choose it random, we don't care, and Alice's bit. But Alice's bit is chosen independently of Bob's view. So the resulting bit is always gonna be random. Okay, that's not the interesting part. The more interesting part is, what about an Alice that tries to bias the bit? Okay, well, here's one thing we can easily say. So if the hash function H is actually injective, so there's no collisions, then actually Alice can't bias the bit. Why is this? Well, in the case where the hash function H is injective, the hash perfectly commits Alice to BA. There's no message she can send in the last message other than the BA that she committed to, if H is injective, because there's only one pre-image. And remember that BB, Bob's bit, was chosen independently of whatever Alice sent. So Alice sends a message, it commits her to BA, and then Bob chooses this random BB. So no matter what Alice does, this BB is going to be random and independent of BA, and so the XOR is going to be random. But this is actually no good for us, because if H is injective, that breaks our argument of security against Bob. Right? If H is, remember, for security against Bob, we use the fact that BA was information theoretically hidden to Bob. But now we're saying, well, actually H information theoretically reveals BA to Bob. So we can't use this result in conjunction with the previous result to say that they both can't bias. Okay, so what about, what if H is collision resistant? Well, in the classical world, actually, that turns out to be enough. So in the classical world, no matter what Alice does, she's unable to bias this bit, just based on the collision resistance of the hash function. And why is this? Well, I'm not going to give the proof, but very intuitively, suppose that Alice is able to actually bias the bit. So that means probability of B equals 0 is greater than a half plus epsilon for some non-trivial epsilon. Well, remember that so basically she's trying to match Bob's bit. And half the time Bob's bit is 0, half the time Bob's bit is 1. And because this probability is greater than a half, there must be significant weight on both cases, both when the case where Bob's bit is 0 and when the case when Bob's bit is 1. And that means that she's actually able to open her hash to both BA equals 0 and BA equals 1 with non-trivial probability. So there's some non-trivial probability in both cases that she's able to open her commitment to that bit. But that gives two different inputs to the hash function h that hash to the same value, the one that she sent in the first message. And that gives a collision. So if everyone is guaranteed to be efficient, there's no way to actually do this by the assumed collision resistance of the hash function. Okay, so what happens when we move to quantum is that actually we have to throw away everything. Why? And this is because the process, so now Alice is some quantum algorithm, and she sends this, this commitment H to Bob, and she has maybe a quantum state left behind that she then measures in the final message to get the opening that she sends to Bob. Well, producing these two openings, we know that Alice is able to produce an opening to 0 with non-trivial probability, and we also know that she's able to produce an opening to 1 with non-trivial probability, just because of this, because her overall probability is greater than a half. But the process of producing these may be non-commuting measurements on her state. And what this means is that Alice may be able to open to both 0 and 1, but can't do both at the same time. That the moment she tries to open to 0, she destroys her state and she can't open to 1, and the moment she tries to open to 1, she destroys her state and can't open to 0. And this issue actually has been long recognized, goes back almost 30 years. And it's called rewinding. This is kind of the cryptographic term for how you would prove the security of this coin tossing protocol. And it's been long known that rewinding is problematic when we move to a quantum setting. Okay, so the question is, okay, the argument that we had doesn't work. So the question is, does collision resistance nevertheless in a quantum world justify the security of the coin tossing protocol quantum? And this was a toy example, but this is actually really fundamental and important to the understanding the security of cryptography in a quantum world. Just totally classical cryptography in a quantum world, because similar arguments are used extensively in, for example, signature schemes, which are one of the major things securing our digital lives. And so basically the idea is when we move to a quantum world, we're going to be upgrading all of our cryptographic building blocks. We're going to be replacing our broken crypto systems from the classical world with ones that are presumably secure against quantum attacks. So maybe we have some hash function. I don't know, maybe Shor's algorithm breaks it. We throw it away. We get a new hash function, and it's going to be collision resistant against even quantum adversaries. And the question is, now that we have this thing, can we use it as a drop-in replacement in all the protocols we build from it? And depending on the answer to this coin tossing protocol, the answer may be yes or no. If we can't get a coin tossing protocol to work from collision resistance, that would actually say, no, we can't do this. We can't just use a drop-in replacement. Even if we upgraded everything to post-quantum, we may still end up ultimately being insecure. Okay, so those were my 3 questions. And now I'm going to start answering them. So I'm going to go in reverse order and start with this last question about coin tossing. And the answer turns out to be that actually this is a problem, that, or at least we believe it's a problem, that you can have collision-resistant hash functions for which the coin tossing protocol fails. And these are something that I'll call equivocable hash functions. So there was a result from a number of years ago that said, relative to a quantum oracle, so we're moving to an imaginary world where we have an oracle in the sky that implements some black box unitary. And relative to this quantum oracle, there does exist a collision-resistant hash function. It's collision-resistant even against quantum adversaries, even against quantum adversaries with respect to this that have access to this oracle. But even though it is collision-resistant, Alice has a near-perfect strategy. So she can always bias the bit to be 0. Okay? What's the idea behind this proof? I'm hiding tons of details here. This is a kind of a gross simplification, but I just want to give an intuition for why this might be true. So the idea is, let's start in our oracle, right? We're in this imaginary world where we have an oracle. We're going to start with a random compressing function, big H. So H is just going to be a classical random function that you can query in superposition. And what we know is that H is actually collision resistant. Okay? So that's good. So we have our collision resistant hash function. And now we want to show that the coin tossing protocol is broken. But it turns out that actually, so far, the coin tossing protocol works. So if this is your hash function, is just this random oracle, actually you can show that the coin tossing protocol does work. So what we're going to do is we're going to try to break the coin tossing protocol without breaking collision resistance. And the idea is we're going to define this new oracle U sub H that's a quantum oracle, and it's going to this oracle is going to reflect around certain states. What are the states? They're basically the uniform superposition of all pre-images of a given hash. So for any possible output of the random oracle H, what the oracle U sub H is going to do is it's going to reflect around the uniform superposition of pre-images for that state, for that output. Okay, and this oracle immediately breaks coin tossing. Why? Well, here's what you do. So you first create the uniform superposition over all domain elements of the hash function. You measure the output, and you send that to Bob. This is Alice's strategy to win. And when she measures her output to get this little h, her state collapses exactly to psi h, the uniform superposition of pre-images. Okay? So now later, okay, so she sent her little h, and now she gets the bit b from Bob. And what she is trying to do is come up with a pair b comma r, where this b matches Bob's b, and it hashes to the little h. And she can actually do this using amplitude amplification. So she has the ability she has this projection onto the first bit being 0 or 1, and she also has this ability to reflect around psi h. And using amplitude amplification, or adapting Grover search, you actually can do this. You can move the state to the psi hb state where all of the mass, or essentially all of the mass, is has the first bit matching Bob's bit. So she'll do this, and then she just measures and gets b comma r, which she sends to Bob. Voila, she just won the game. Okay, so we're technically not done. You also have to show that having access to this U sub H oracle doesn't break the collision resistance of H. The prior work showed that H is collision resistance just if you're given H, but you're given this oracle U sub H that makes really non-trivial use of the random oracle, and maybe having that breaks things. But you can show that it doesn't. And the intuition is that you have this U sub H, and it's allowing you to kind of massage the state and move to different superpositions of pre-images, but there's no obvious way to actually get two pre-images at the same time, right? You're moving your one pre-image to a different set of to a different superposition over pre-images, but you still only have one superposition over pre-images. There's no obvious way to generate two. And this can be formalized and shown to be the case. Okay. Okay, so we know an answer to question 3 already, which is that relative to a quantum oracle, actually this is a problem. And this is already enough to get cryptographers worried about this question and trying to develop new approaches to overcome it. But a really natural question is there a classical oracle separation? I think this is interesting just from a foundational perspective, but also maybe, like we're dealing with classical objects here. I have a classical hash function that we're talking about. It's really kind of weird that we're moving to a quantum oracle setting to reason about a classical hash function. And so a classical oracle separation might be a bit more evidence that there is a problem. And then another issue is that, okay, well, this is an oracle setting. It's still pretend. And really what you want is an oracle-free separation. This would involve some sort of cryptographic computational assumptions. And this would really be you really have to pay attention to this, because this is now real world, right? If you have a hash function in the real world based on some computational assumptions, where this fails, now it really says you have to revisit everything.
Sorry, I got lost somewhere. Is there any bearing of this on your original question of can you send the same message? Two people?
Yeah, yeah, that comes,
All right,
yeah.
that's gonna come.
They're all related.
All
and
right,
that's,
all right.
that's coming next. Yeah, we're gonna answer them in reverse order though.
All right.
Sorry, another question.
Yes.
Yeah, so you mentioned that, this is secure when you don't have this oracle, and it's no longer secure when you have this oracle.
As a coin tossing, the coin tossing protocol is insecure.
in the coin toss.
Yeah.
Protocol. And I'm assuming this hash function is public.
Yes, anyone can query it.
So you're saying that the earliest theorem where this is secure is assuming that implementing this oracle, given this hash function, is actually very different.
Well, so we're modeling the hash function as a random oracle. So it's just this exponentially large random function.
I see. Okay.
Yeah, and the only way, yeah, so you're not it's a model where it's a pretend world, right? Where we're saying all you can do on these, you have this hash function, all you can do is just monolithically evaluate it. You don't actually have code for it. In real life, the hash function is actually a thing that you'd have a circuit for.
Yeah.
Yeah, so that's why these oracle kind of impossibilities they tell us something, but it could be that, there are cases where oracle results just break down when you move to the real world. Do we know that these equivocal hash functions, are they one of those cases where things break down, or are they a case where actually, it is a problem in the real world? Okay, so 5 years ago, my co-authors and I, we made progress on answering the first of the challenges, presenting a collision-resistant hash function where Alice can win relative to a classical oracle. So instead of having unitary, we gave a classical oracle. Except there was a bug, and this was pointed out to us by James Bartusek, and the bug was totally fatal. Like there was no recreating the argument from that work. The construction maybe works. The oracle that we give may still enable this collision-resistant hash function where the coin tossing protocol is broken, but we just don't know. We don't have a proof. We don't have an attack. Okay. So, and this brings me to the very recent work by Omri Shmueli and I, where we first fixed, well, we didn't exactly fix the proof, but we reproved the broken theorem from before. So we showed that relative to a classical oracle, there is a hash function where Alice has a perfect strategy. And then we went even a step further and said under appropriate cryptographic hash functions, you can do this in the real world. And these, I'll tell you what the assumptions are later, but they're somewhat accepted assumptions, relatively standard in today's terms. Okay, so how do we do this? So we're going to roughly follow the blueprint of the prior work, but now we have to somehow realize this unitary use of H using a classical oracle and do so in a way that doesn't just completely break collision resistance, right? We still need the collision resistance problem to be hard. So what do we do? Well, in the 5 years ago, what we did is we said, okay, well, we're going to make H, our hash function, it's not going to be a random function anymore. It's going to have a lot of structure. And it's going to be something that we'll call a code set partition function, where the preimage sets, for each image, the preimage sets are affine subspaces. I'm being a little ambiguous, but like think of it, interpret your input as a vector in f2 to the n or something like that. And the preimage set for any particular output is going to be an affine subspace, or a coset of a linear subspace. Okay, and actually constructing these is not exactly trivial because these cosets partition the space, but they can't intersect, and somehow they need to so you're fitting all these subspaces in there, and you also want to make sure that if you're not careful, if all the subspaces are parallel, you can actually use period finding to find collisions. So you have to be, it took some effort to design this H. And then what did we do? We provided this oracle Q that tests for membership in the orthogonal subspace. So for each preimage set, we can take the orthogonal subspace and give an oracle that tests for membership in that orthogonal subspace. All right? And these were our oracles. So using these oracles, we can show that you can break the coin tossing protocol. And really all we have to do is implement this reflection operation, right? We have to show that we can implement the operation that reflects around the state psi h, the uniform superposition over preimages. How do we do that? Well, okay, so first we can test that we're in the support of the uniform superposition of preimages just by computing the hash function for ourselves. And now remember that our superposition of preimages, our preimage set is just an affine subspace. It's a linear subspace, it has a lot of structure. So what we're going to do is we're going to apply the quantum Fourier transform to this superposition, whatever it is. We're hoping it's this, but maybe it's something else. We're going to apply the quantum Fourier transform. And now it turns out that if you apply the quantum Fourier transform to this state, where it's a uniform superposition over the coset, or over the affine subspace, when you take the Fourier transform, you're going to exactly get a uniform superposition over the orthogonal subspace just with some phase. Right? So that's what we do then. We have a membership check for the uniforms for the orthogonal subspace, so we just check that you're actually in the support there as well. And what Aronson and Cristiano showed, they were building a quantum money scheme, and they showed that actually the only way to pass this verification test is if your original state is in fact psi h. That this is actually a projection onto the state psi h. All right, and once you have a projection on the psi h, you can implement a reflection about psi h, and then you can complete the proof. Okay, so this gives Alice's perfect strategy. Now there are some problems with this approach. So one is we introduce extra structure. So this hash function h is no longer just a random hash function. It's a very structured coset partition function. A priori, who knows if it's collision resistant or not? The previous theorems definitely didn't apply. And then we also give this oracle Q that it's potentially applying more. So we know if h was random, so we're even going to forget for the moment that h is not structured. Previously, it was shown if you give u sub h, that doesn't break collision resistance. But here we're giving something else. We're giving this oracle Q. And maybe giving out this oracle Q allows you to do more than what you could have done with u sub h. So the previous guarantees just said nothing about this approach. And so we needed brand new arguments to prove the collision resistance of h, and turns out our brand new arguments didn't work. Yeah, our proof was fatally flawed. I still think the construction works, but there's no proof. Okay, so now I'll get to our approach, our result, the new stuff. And this is a slightly different construction. The idea for this approach actually was due to James Bartusek when we had this quantum money workshop almost 2 years ago. And the idea is, so we want to relax the structure a bit more to hopefully make things easier to reason about. So we're going to leave the hash function unstructured. So we're going to go back to h being a totally random function as opposed to this highly structured coset partition function. We're going to make a minor assumption that all the preimage sets have the same size and their powers of 2. But aside from that, it's basically unstructured. And now what we're going to do is we're going to choose, for each possible output of the hash function, we're going to choose a random affine subspace S sub h whose size matches the number of preimages. And importantly, these subspaces, they just live in a completely different domain than the set of inputs. So in a coset partition function, this SH is exactly the preimage set. And here we're going to say it's actually a set in a completely different domain. All right. And what we're going to do is we're going to provide 2 oracles. So we're still going to have the membership test for S sub h perp, the orthogonal subspace. And then we're going to give you an oracle that allows you to go between your unstructured preimage set and your structured S sub h. So we have this oracle P that allows you to go back and forth between the actual preimage set and S sub h. Okay, and this lets you do Alice's attack, right? And the reason is that you can still project onto psi h. So now psi h is a uniform superposition of preimages. It's unstructured, but you can use P to map your preimage set to S sub h, and then run the verification from before. Okay, so we can still project on to psi sub h, and therefore Alice can still run her attack. But now so the hope is that h has less structure now because it's just this random function. So maybe it's easier to analyze. And this was James's original idea for why he suggested this. But it turned out a priori it was very unobvious how to reason about this because yeah, fine, h has less structure, but then we just add this oracle P that kind of makes it have structure and ultimately anyway because you're mapping these preimage sets to affine spaces anyway. Okay, so what Orme and I did is we actually went and proved this. I don't have nearly enough time to get into any of the details of the proof, but very, very, very roughly, so we need to show collision resistance. How do we do this? So first, we show that you can kind of without loss of generality ignore the oracle Q for testing the orthogonal subspace. And then we actually go even a step further and show that basically you can remove P as well. This oracle that maps between your preimage sets and your affine subspaces. And essentially what step 2 is doing is it's reducing to the collision resistance of coset partition functions. Okay? And these 2 steps, basically we observed that the structure allows you to do a random self-reduction where you can take one instance of the oracles and create a brand new fresh instance of the oracles. And using this random self-reduction with a lot of other tricks, we're able to first eliminate Q and then do this like worst case to average case reduction. Okay, so now we need to justify the collision resistance of many-to-one coset partition functions. Well, I said previously many-to-one coset partition functions are hard to reason about because you have to somehow fit all these cosets or all these affine subspaces together. But we show that in the worst case, coset partition functions are collision resistant. And actually this part's easy. So the observation is that if you have a random 2-to-1 function, it's actually automatically a coset partition function. Any 2 points in Z2 to the n form a subspace, just the line passing through them. Now we need many-to-one. 2-to-1 isn't going to be good enough for technical reasons I won't get into. But you can just have a bunch of random 2-to-1 functions evaluated in parallel, and this gives you a coset partition function that's many-to-one. And importantly, like we don't care about the structure, right? Because step 2 said we can have, all we need is a hardness of a worst case instance. So we don't care about the structure of the coset partition function. Doing this parallel repetition thing is fine. And that's basically the proof in the oracle setting. And then we gave a proof in the oracle free setting. And the rough idea is we have all these random choices in these oracles. First thing we're going to do is we're going to pseudo-randomly generate them using cryptographic pseudo-random functions and pseudo-random permutations. So now it's efficient. So we're compressing this exponentially large randomness, like all the choices of the affine subspaces and so forth. We're compressing it into something small and efficient. And then we're going to replace the oracles. Instead of just handing out an oracle that computes the function, we're going to obfuscate it using something called indistinguishability obfuscation. And this is just a method to take code that maybe has cryptographic tools inside of it and scramble it so that morally what you should think of is like it's acting as a black box. Now in reality it's not, but that's the intuition. So we throw it inside an obfuscation, and then each step in our proof we replace with an appropriate cryptographic step where we prove that we can actually make this transition to the next step under the appropriate computational assumption. And this was highly sophisticated, required a lot of interesting new techniques that actually are interesting kind of beyond the scope of one-shot signatures, because we had to show how to obfuscate pseudo-random permutations, which was previously unknown. Okay, so in the last 10 minutes, okay, so that was question 3, right? So question 3 says, actually, you really do need to worry about this issue with equivocating. And now we're going to see, actually, we're going to flip this on its, oh, yes.
Just before you go to the previous section, you just need pseudo-random permutations in IO? Like, I thought I
mean, one-way functions in IO, and we need sub-exponential security for technical reasons.
I thought you needed LWE.
You're right, yes. We also need LWE for also some like rather technical reasons. Yeah, basically this underlying, so basically everything works except that we need a special kind of collision resistant 2-to-1 function. And it's not inherent that you need LWE for that. So like step 3, basically, getting this coset partition function and justifying its hardness, that's where the LWE comes in.
Like some trapdoor cryptography kind of thing? Or just
yeah, we don't care about the trapdoor, or I mean, we do care about the trapdoor in the proof, but yeah, it's based on these claw-free.
I guess what I want to ask is, are we using the public keyness of LWE in any way, or just like?
Yeah, because the hash function has to be publicly evaluatable. Okay, so yeah, now that we've seen that actually you can have hash functions that are even if they're post-quantum, your protocols built on them can fail. So that's bad news for crypto. But we're going to turn it on its head and make it good news for crypto. And what I'm going to show is that equivocal hash functions actually give you one-shot signatures. So now we can answer question 2 in the affirmative. So remember what a one-shot signature is that we have this adversarial setup that sends verification keys to Alice and Bob. These are guaranteed to be the same. The adversary keeps some secret quantum state for himself. And now the adversary tries to send different messages to Alice and Bob. And Alice and Bob, without communicating, can guarantee they get the same message. Okay, so this showing that equivocal hash functions give one-shot signatures has a long history, but it's actually very simple. So here's the idea. So the honest setup, so to guarantee this non-triviality condition that the adversary, if they're fine sending the same message to Alice and Bob, they can do it. What you do is you just honestly sample uniform superposition over, you create assumed uniform superposition over preimages, you measure it, you get H, and H is going to be your verification key. So your verification key is the first message in Alice's strategy for this equivocation game. And whatever the state she has left behind is going to be her secret key, right? This superposition of preimages of H will be her secret key. And now, if she wants to assign a bit B, so we're going to say the messages sent to Alice and Bob are just bits for now. If she wants to assign a bit B, she runs the second step of Alice's protocol for the Alice's attack on the coin toss thing. And so she equivocates the hash function into a B, R pair that hash to H, and the signature is just that R. And then the verification, you just check that the signature and the bit hash to whatever the verification key is. Right, and we can extend this to multiple bits just by parallel repetition. So if the adversary is able to cheat on this, they break the collision of the hash function because it means that they're finding a pair of messages with differing first bits that hash to the same thing. And so that's it. That's one-shot signatures from equivocal hash. Okay, and now let's answer the first question, which is how do you send quantum money with classical communication? Okay, and this is a very nice protocol. So first, what's the quantum money scheme? It's a special quantum money scheme. So the Mint is going to publish a verification key VK star, and this is for just any arbitrary signature scheme. I haven't defined what a regular signature scheme is, but it just allows you to sign messages and authenticate that you were the one who signed them. So there's nothing quantum going on with the Mint yet. And then the signing key that allows the Mint to sign messages, they'll keep secret. And now, how do you create a banknote? So what you're going to do is you're going to run the first step of the equivocation game, where you're going to run the setup for the one-shot signature and get a secret key, public key, secret key verification key pair. It's quantum secret key, classical verification key. And then you're going to sign this verification key using the Mint's secret key. So this is a classically generated signature on VK. So VK is now the thing that gets signed by VK star, by SK star. Okay? And intuitively, what's happening here is anyone can generate SK VK, but because the Mint signed VK, that's how you authenticate that actually it came from the Mint and it wasn't, someone didn't just make it up from scratch. How do you verify? Well, you first verify the signature that says, okay, this VK actually was authenticated by the Mint. And then you just check that the SK can actually sign messages relative to the one-shot signature scheme, relative to VK. And that's it. That's verification. And you check that the secret key can sign messages and that the verification key was actually legitimately signed by the Mint.
So basically, going to the ATM means engaging with a classical communication with the bank and then doing something in your local quantum computer.
Yes.
Will end up with a money state in your quantum computer.
Yes.
And hopefully is uncopyable.
Yes, exactly.
But is this just with the particular coset-based money scheme?
No, this is fully generic as long as you have a one-shot signature.
Ah, I see.
Yeah, any one-shot signature will give you this. Now, the only way we know how to build one-shot signatures is through this coset.
I see.
thing,
I see.
but,
Got it.
Right, and okay, so how do we send this with classical communication? Well, just at a first glance, the Mint can actually send this with classical communication. Why? Remember, anyone can compute this part for themselves, the SKVK. So if I'm going to the ATM and I want to withdraw money from the bank, I'm just going to create my own quantum money state for myself locally. this is the whole quantum part, right? This is the only bit that's quantum. I'm going to create it locally. And now I'm going to send VK to the mint and say, hey, mint, give me some money by signing this VK. And the mint will sign using their secret key. And then they'll just send me the sigma here. And so this whole tuple, then, I will get the tuple, but the only communication between the mint and myself is VK sigma.
Sorry, why can't I then counterfeit?
So why can't you counterfeit? Well, actually, before I get into that, let's say how Alice. So okay, it's fine. The mint can send money to people using classical communication. But remember, that's definitely interesting and important. But I want to go a step further, and I want to allow Alice to then send the money to Bob with classical communication. And this is what really distinguishes this from like remote state preparation kind of setting, because here Alice doesn't know how to construct this state, and yet she's somehow going to send it to Bob. And the idea is, well, just like before, Bob is going to create his own money state from scratch. He can do that. Anyone can create the money state. It's just some protocol. And he's going to send the verification key that he gets, VK prime, to Alice. And now what Alice does is she signs the Bob's verification key using her quantum secret key under the one-shot signature. And because it's a one-shot signature, I mean, we don't know how she signed it. Maybe she's trying to keep her money and send it too. But we know that like whatever she does, her state has to be destroyed. That's the guarantee of the one-shot signature. So she signs his verification key, sends the resulting signature to Bob. And now what does Bob have? He has a quantum secret key that can sign messages. He has the associated verification key. He has this signature saying that the mint signed VK. Okay, but that's not his VK. But he also has a signature that says, well, someone signed relative to VK, his VK prime. All right, and so to verify this, you verify this signature, and you verify that SK prime signs messages relative to VK. All right, and why does this work? Why can't you forge? Well, in general, okay, so as I'm sending this money around, basically what's going to happen is the money state I get is going to be this chain. It's going to have whatever the last generated SKVK under the one-shot signature was. And then there's going to be this chain of signatures going from VK star, the mint's verification key, all the way to my local verification key. So that's in general going to be what a money state is. And so you can kind of imagine the mint signed, made 4 money states, send them to 4 people, and then they send them and so forth. And now imagine though, at the end of the day, somehow there's 5 money states hanging around. Well, that means somewhere there was a branch in one of these chains. But a branch in one of these chains actually means, so there was a verification key here, and then the money states here are going to involve 2 different signatures relative to the same verification key, and that's going to break the one-shot signature guarantee.
I mean, one thing that's conceptually weird is like this only seems to make sense in a world where the bank, sort of keeps track of people's bank accounts, how much money they have. Right?
No, we don't. No, they don't need.
Okay, because otherwise, like if the bank doesn't keep track of anything, then why can't you just keep requesting this bill from the bank over and over?
No, I meant like think of this as literally a replacement for the coins in your pocket.
Okay.
Right, except they're quantum states.
Okay.
Right, so the mint, all they know is that they've issued $1 billion.
Sure.
Right,
Mm-hmm.
and the guarantee of the one-shot signature though is that there will only ever be $1 billion that pass verification.
Okay.
Right, because if there was $1 billion, so each one of these paths here is going to be the kind of the path of $1 as it's being handed around between different people.
Mm-hmm.
And if there's ever $1 billion and $1, that means that one of these paths had a split. But if one of these paths split, remember that this has a signature on this has a local verification key. This has a local verification key, and to be valid, these local verification keys had to be signed by this verification key. But that means there's 2 signatures relative to 1 verification key, and that breaks the one-shot signature guarantee.
And okay, and the bank can just decide separately when someone is worthy of engaging in the classical interaction that gives them the money.
Yeah, whatever protocol they use to issue $1, they
Yeah.
can run the same protocol, but now it's just fully digital.
And then if they don't want to do that a second time, then they will.
Yeah.
Maybe they need to get some gold in exchange or something.
Right. Yeah, question?
Is there an easy way to see if it's possible to like not have everybody carry around the entire history of their money or?
Yeah, that's a great question. So okay, so there's one annoying thing here, which is that, you know, let's say that your dollar bill has changed hands 100 times. Well, your banknote now is going to have 100 verification keys and signatures in it. And you would, in general, not like that. So we have cryptographic solutions for this. Basically, you can batch all of these signatures together and do what's called a succinct non-interactive argument to just kind of collapse them into a short string that's also efficiently verifiable. We kind of didn't pay attention to this, but there's a sort of a subtle issue that you know, okay, if you're gonna keep batching these as you go, you need a particularly strong guarantee on your non-interactive arguments, and you know, a lot of them don't guarantee that. But they're like, at least heuristically, you can do that. Relative to an oracle, it's trivial to do that. Not 100% sure if we can, you know, do it from obfuscation and one-way functions. But that, yeah, we have cryptographic solutions to compress. Yes.
Is the adaptivity the problem you're mentioning?
It's the recursive composability. So imagine I batched a bunch of signatures down to a snarg, and now I get more signatures, and I want to batch those signatures together with the snarg, and I want to do it again and again and again. Generically, you can always do recursive composition a constant number of times, but if you're going to do this more than a constant, there's a question of if there's security there. We didn't really pay attention to this. I don't know if there's easy solutions, but that's, you know, that's how you would go about doing it.
And again, just to clarify, the one-shot signatures also imply that you can send the message to two people that has to be the same?
Yeah. I mean, that's kind of how I defined it in this talk.
Okay, that's that. Okay, good.
Yeah. Okay. Any other questions? Yeah.
So this parallel repetition to sign on messages increases the length of the secret key a lot. Is it possible to have like a one-shot signature scheme where the secret key is like some fixed length that you can sort of sign arbitrarily?
I'm not sure. I mean, at the end of the day, if you're only caring about like asymptotics, it all gets absorbed into like security parameter kind of stuff, because you can you know, once you signed messages that are security parameter length, you can just use collision resistant hashing to sign arbitrary lengths. But yeah, like, you know, concrete efficiency is open.
Okay, let's thank Mark for the nice talk.
All right, thank you.
We have another coffee break, and then we are back here for a talk by Scott.
Slides? I am now.
I saw you. Yes.
Yeah, I'm now. Yes, early. I got 25 minutes.
You never got to talk. I know.
Proved some new results.
Oh, that's cool.